Hello, welcome back. In this video, we are going to continue seeing about the Yang data types. We will cover the bit level data types in this video. We will begin with a short recap with an overview of the Yang data types that are available. We will then cover each of the individual bit level data types, namely bits, binary, and Boolean. As we saw earlier, the Yang built-in data types can be broadly classified into 5 categories. We saw the first 2 categories, numbers and characters already. Now we will focus on the bit level data types. In the subsequent videos, we will cover the reference types and the special types. The bits data type represents a set of bits. Each position in this series can be marked and given a name. This is normally used to represent a set of flags which is used to indicate as on or off depending on the value of the bits. The position number can be indicated with an optional statement called as position, and there can be a total of 2 power 32 positions that can be represented by this data type. Let us take a simple example. All of us have mobile phones in which certain functionalities are on and off. I have taken example of 5 such common services: Bluetooth, Wi-Fi, mobile data, screen rotation, and the torchlight. If we were to represent this as a series of bits, the example you see on screen is one form. We have bit position 0 through 4 assigned to each one of these types, and each of these positions can be set to on and off depending on if the service is enabled or disabled. The position statement, as I mentioned, is optional. It need not be specified in every single bit position. The first position is by default assigned a value of 0 if it is not specified. The subsequent positions can either be assigned a specific value or the value is assigned automatically by the system. How? The new value takes the value of 1 more than the highest prior value. As you can see here, the mobile data is following the bit position called Wi-Fi, for which a value of 4 has already been assigned, and prior to that we have the Bluetooth bit for which no value has been assigned. So the Bluetooth bit position is marked as position 0. After that, the Wi-Fi bit position has been explicitly assigned as 4, following which, since the mobile data does not have a specific bit position allocated, it will take the value of 5, screen rotate a value of 6, and again for night light, if the position number assigned is 8, then that will be the value taken. There are some other rules associated with the position statement. The value that a position statement can hold is a maximum of 2 power 32, which is what you see mentioned here. However, if this value is mentioned in a position, whatever subsequent bit positions are named, they must have an explicit value assigned. Otherwise, it will not be accepted. Why is this so? As per the explanation that I just gave, the new value assigned is the highest prior value plus 1. Now, if a position has already been assigned the value 2 power 32 minus 1, then the subsequent values cannot go any higher. So the only option is to explicitly specify the value for each of the bit positions. You can now see the correct way to do this. The first position, if it is assigned the maximum value, every subsequent bit position is explicitly numbered, and this is accepted by the system. Let us now see a short demo of the bits type. We will use the same example that you saw in the presentation. We have the phone services type defined based on the bits data type, and there is a leave my services that is restricting the type to only the value torch. So now we will compile it using pyang. So pyang data types.yang. There are no problems. So it has compiled. Now I will start introducing errors and show you the possible errors that pyang will throw when you make mistakes in it. So I will now try to override this value which is illegal. So I go here and say position 5. So I try to overrule the value in the base type. Let's see what is the error that pyang says. Hold on, this is another error. You are not allowed a semicolon at the end. Let's try again. So see, the given position 5 does not match the base bit position 4. Now let's do something else to see what is the error message that we get. So I now try to add another value, say night light. I try to do something like this. Let us compile now. You see, you cannot extend the base type as you like. You can restrict it to a subset of the values defined in the base type, but you cannot add a new value which is not there in the base type. So here the error message now is the value night light does not match its base type not defined. You see, it is saying that it is not at all defined in the base type and hence you cannot use it. Let us see the example for using the maximum value. As you can see here, I have now defined the 2 power 32 minus 1, the maximum possible value for the Bluetooth position, and I have not assigned a value for Wi-Fi. So what happens now? You try to compile. You get the error message saying 296 is not valid because we have already used up the maximum value possible and now it is required to explicitly assign a value. Now to correct this, now you see it compiles. Why? Now each of these values are explicitly notified and the value does not exceed the maximum value possible for the position. So this is another point to note. If you are going to start with the maximum value or use it at any place in your definition, whatever follows that must definitely be explicitly assigned a value. Why do I say that? I can do this before. Say bit. Oh, so you can see the first position I have not assigned a value at all, meaning it will take the default value of 0. I try to compile, it will still compile. Why? The scenario arises only after you use up the maximum value. Whatever follows is based on the maximum value that has already been defined and a new value is tried to be assigned. Now if you see here, I remove the position number 3 and I try to see if this compiles. See the error message you get. Just because screen rotate is defined after position 2 doesn't mean it will automatically assume the value 3. It is not the previous value plus 1. It is the maximum assigned position value earlier plus 1, and hence you see the same error message popping up. It is trying to assign the value 296, and that is flagged as an error by the compiler. So we go back and assign like this. Now let's see what happens. Is this accepted? Sorry, this is not the error message. Hold on. If you see this, the error message that you will get is position 0 has already been used. Why? The first position, night light, even though it is not explicitly defined, always takes the value 0. We now move on to the binary built-in type. The reason for having this built-in type is there can be scenarios where binary data has to be stored in the data model, but storing it as a series of ones and zeros is generally not a preferred way of doing it. This is because if such a big streams of ones and zeros are put on the wire in the raw format, this is very much prone for error, corruption, and misinterpretation. A lot of protocols have a sequence of ones and zeros as an introductory sequence, and these series of ones and zeros have specific meanings for different protocols. To avoid this, the binary built-in type is available, which encodes such binary data into a form called as base 64 encoding. This base 64 encoding is actually defined by the RFC 4648, where there is a common set of characters that are available, which can be used to represent any series of bits, ones and zeros in a textual format. A textual format is a convenient way of representing this, and this will also ensure that the raw data is not exposed either on the wire, and it will not be corrupted. The form of defining this is very simple. You just state the type as binary. You can restrict it by specifying the length of the binary message. You can specify the number of octets that a binary type leaf can hold. Here I have defined it as a 256 octet message. So depending on the application where you are using, you must define the length accordingly and ensure that the application is aware of the base 64 encoding, and it can derive that value when it is set by a client, and you convert it to the appropriate form for usage. We will not go into the detail of what base 64 encoding is and how it is done, as it is out of scope for the topic which we are discussing. You can refer to the RFC 4648 for more details. I have also given a sample website that is available. You can look at it to see how a binary string is represented in both 64 format, and that will help you understand more. The final type is the simplest type, which is Boolean. It is used to specify a true or a false. The definition is very simple as shown here. The application is obvious. Whenever you want to enable, disable, on or off, you can use this type. So we are using the same example. Earlier we represented Bluetooth Wi-Fi services in a bit sequence. It is also possible to use a Boolean type for the same, to say false means Bluetooth is switched off, true means Bluetooth is switched on, and similarly for Wi-Fi. That brings us to the end of this session. In the subsequent videos, we will cover the remaining data types, namely the reference types and the special types, with examples like the ones we have seen here. Thank you for listening. Do subscribe to this channel for more updates and videos like this. Thank you. Bye bye.